Can someone in the back help close the door? Thank you. Is there any new student just came in this week due to visa problem? Or you? What's your name? Oh, something in. Okay, so you're the one. Then- Oh, Kumahan. Okay. Chen. Yang Yuehan. Oh, okay, okay. Okay. Welcome. Okay, welcome to our physical class. But today we got a quiz. Okay. Welcome you to the quiz. Okay, hope you are prepared. Any questions from last week, last tutorial, last lecture? Any question you want to ask? Any question on previous material. Yeah, because you are the first class of the week, so sometimes I tend to talk. Sometimes I tend to talk less organized. So if what I said confuse you, then you should ask on the spot. Because sometimes a bit disorganized, I try to say a lot of things at once. So after each class, then maybe I'll get better and how to put those things together. Or sometimes, yeah. So make sure you keep asking me and then just raise your hand and then stop me anytime. It's like if I going too fast and then or I say something not making sense. Okay, feel free to stop me. So okay, so today we were going to a new chapter called the number theory and cryptography. Okay, so number theory and cryptography also lasts for 2 weeks. So this week we'll talk about more on number theory, and then next week will be on cryptography. And then this 2 weeks, maybe you need to study a little bit harder because straight after this 2 weeks is the midterm. Okay, so make sure you keep up with yourself. But of course, I will give some hint for you to like um, focus on what to study. Right? Okay. Okay. So for this number theory, what we were looking at is this modular arithmetic. Okay. Before we learn counting to infinite, we will try to count finite thing first. Okay. For example, in the set theory, we gave an example of set, which is the set of clock numbers. So when it is the hour 13 is actually 1 p.m. and then hour 14 is a 2 p.m. Okay, so these are more 12. Okay. So for example, if okay, yeah. Yeah, for example, if in like what is for example, what is let me think. What is 12? What is uh 4 hours after 12 p.m.? So if you do 12 plus 4 is 16, but mod 12 is 4. Okay. So this is one example of modular arithmetic, and later we will introduce this concept. So before we introduce the concept of this uh, modular arithmetic, we have to know what does it mean to be a division. Okay. So let's take two integers. So take two integers, and one of them I want it to be non-zero. Okay. And then we say that A divides B. Yeah. So only non-zero element divide another element if there's this another integer such that B equals to AC. Okay. So if you divide a number, yeah, that's mean you can multiply another integer to get this number. Okay. Or equivalently, b over a is an integer. Okay. So when I go, and maybe I do example first, and then we introduce more terminology. So, for example, 2 divide 6. Why? Because 2 equals to 2 times 3. Okay. So 2 doesn't divide 7, right? Because 7 over 2 is 3.5, which is not an integer. Okay. So let's introduce more. So this one is continued from above. When A divides B, we say that A is a factor of, okay, or divisor of B. Okay. And then the other way around, B is the multiple of A. Okay. So it's like A is a part of B, okay, divided or a factor of it. And B is a multiple of A because you multiply something else to get B. Make sense? So we can write, yeah. Is it too small? Too small? Huh? Can see a lot? Okay. Let me know if too small. So the notation A divides B, so it's a straight line. A divides B, denote A divide B. Okay. If it doesn't divide, then we will slash in the when. Okay. So that's not divide B. Okay. So for example, we will write 2 divide 6 or 2 doesn't divide 7. Okay. Okay. So this is a division. So what can we do? So let's see. So let's take 3 integers, okay, and not all 0. Let me write correctly. So where one of them is not 0, okay, then you can take the non-zero integer. If it divides B, okay, and it divides C, then it divides some of them. Okay. I think this is a natural question you want to ask. If it divides some different number, does it divide the sum, or does it divide the product? Let me see. So if A, then C, for O, C, okay. And then if A divide B and B divide C, then A divide C. Okay. So let's see what is this statement means. Okay. So try to suppose. So in the first case, we suppose A divide B and A divide C. Okay. So we want to show that A divide B plus C. Okay. So remember what's the definition of dividing? So what does A divide B means? B is equal to what? Huh? Yeah, so B is equal to A because C is now used, so we don't use C anymore. So maybe we use A equal to some K. You want to use K? Maybe use M. So M or some M in Z. Okay. And similarly, because A divides C, right? So also we can find maybe N such that C equals to AN, right? So uh so let's do some uh one second. Maybe some maybe let's understand what we want to get. Okay. So when you say A divides B plus C, what do you mean? So by definition, it means B plus C equal to A times some number, let's call it maybe wait what? H? H. Okay, let me call H. So you want to find this H, okay? So let's find the H, okay? So maybe let's put together what we have first. Then we have B plus C equal to AN plus AN, right? So you can factorize, right? So when you factorize, you get n plus n times A. Maybe on this side. So you add two integers together, you still get a integer. So this is the H you have. Okay. So you can conclude that hence A divide B plus C. Okay. Make sense? Okay. Sure. Let us try next one. See whether we all got it or not. Okay, let's prove the second one. So suppose A divide B. Okay. So we want to show A divide BC for all C. Since it have to be true for all C, then we have to take start with the, what is that? Yeah, take any, you want to verify for any C in Z. Yeah. By assumption, yeah. So what does A divide B means? B equals to A times some integer. You call it anything you want. That's fine. So what do you want to get? So let's try working backward. What does this mean? So this means BC is equal to A times some H. Maybe some H, call it H. So you need to find this H here. Okay. So since we got B, we got C, then let's try to take the product of them. Then we have BC equal to A MC. Okay. Which means BC is A times MC. So if you multiply two integers together, you still get an integer. So hence A divided BC. Okay. Okay, if I really want to be pedantic, I write since M C is in Z. And then maybe I also write here since M plus N is in Z. Okay. 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 I'm gonna try 3. Okay, maybe just do 3. So suppose A divide B and B divide C. Okay, we want to show that A divide C. Okay. So since A divide B, B divide C, so we have that B is equal to A times sum N or N in Z. Okay. And then C is equal to B times N or sum N in Z. Okay, similar to part 1. So what's the goal? The goal is to show that C is equal to A times sum H for H in Z. Okay. So since we got C equals to B N, okay, we also got B equals to AM, right? So AM and N. Okay. So we can use associativity. So we get A times MN. Okay. Hence A divided C is MN Z. Okay. Okay. So why are these important? The most important thing is this. So corollary one. Okay. So corollary is proof from theorem. So if A, B, and okay, let me just write A, B, C in Z, okay, and A not 0, such that A divide B and A divide C, then A divide the multiple of B plus the multiple of C, okay, for any Mn. Okay. So should I prove this or left this as an exercise? So you want to try do this or huh? You want to try do it on your own, huh? No. What? Okay. Sure. Since you want me to do, then maybe we can do together. Okay, so this corollary came from theorem, right? So let's recall this theorem first. Let's recall the theorem here. Okay, it's good that you say you don't want so that I do, otherwise I just skip. Okay, so corollary means it follows from this theorem, so we need to think out of a way to use this theorem. Okay, so let's think what's going on here. So you have A divide B, A divide C. Okay. So say you got part 1 have similar condition, right? So you can divide the sum of them, right? Okay, cool. So, but the difference between part 1 and this corollary is you got extra M here, extra N here, right? So how you going to how you going to show that it also divide multiples of B and the sum of multiples of C, right? But you also know that if A divide one's number, it divides the multiple of them. Okay, so let's try something. Okay, Okay, I didn't write the proof in my note as well. I also think on the spot one. So I'm like you. Okay. So, okay. So let's write first. So suppose, okay, I don't want to write this line. Okay, this line is given. So I just write these two first. Okay. So because these agree, so we just left it there in the statement of the theorem, and then we suppose something that we want to use. So suppose A divide B, A divide C. Okay. Suppose A divide C. Okay. So I think I want to introduce this M and N first. Okay. So since it's divide B, it divide multiple of B. Since it divide C, it divides multiple of C. Okay, right. So I can say by theorem 2. Okay, since A divide B, A divide M B or M in okay, maybe I don't say for OM, so should I say for OM? Okay, I think should be fine. So for OM, okay, this one I just use part 2, right? Because I satisfy this equation, then this has to be true. Okay, logic. Remember logic. So this have, if this have to be true, this have to be true. If then, okay. So similarly, we have A divide NC for all M plus for all M Z. Okay. I just do the same, use the same part to different thing. Okay. I divide this, then I can divide the sum of them. Okay. So now by theorem part 1. Okay. Since A divide NB, okay, and A divide NC, okay, we get A divide MB plus NC for all M and Z. Okay, which is what we want. Does it make sense? Okay. 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 So done. Okay. Any question? No? No? Very straightforward, is it? Okay. Okay. So the key point to take away is if you divide two numbers, so you divide the sum of multiple of them. Not just sum of them, but sum of multiples of the individual terms. And then you can take different multiple. Here, M and N can be different. Okay, this one is a key to the next step. Okay, next, before we jump into the mode, we need to know this the division algorithm. It is stated as a theorem in the book. I'm not sure, but I won't do the proof here. I'm not sure the textbook or no, forget already. But there's a proof for it, but we won't do it here. But what you need to know is to understand this statement here, this theorem here. So the idea is simple. You should know how to do division since primary school, I think. Right. But the statement is like this. So if you got an A, yeah, so there's a unique, and remember unique, the existential, and then exclamation mark, there's one, okay? There's one integers Q and R. We got condition on R. So the condition on R is less than equal to, did I copy something wrong? I think no. Okay, to D. Okay, so what is the relation between A, Q, R, D? Okay, so this equation here, sum it all up. So this is A equals to DQ plus R. Okay, so what does this mean? What does this mean? So for example, let me do an example so you can keep one example in your mind. So just now we say that, oh, okay. Sorry. Sorry. Yeah. Okay. Wait. Let me tell something. Hey, this one is going on. Let me, I'm sure got some urgent stuff, you know. Not sure. Hopefully there's no urgent stuff. Okay, hey, where am I? Gone. Okay, it's fine. Okay. Let me come back. Where am I? Okay. So yeah, just now we said that 7 is not divisible by 2, right? So we can say that 2 is equal to uh, 2 times 3 plus 1. Okay? So you see, this, you can think of this part is the D. Okay? This part is the R. Okay? So what's unique? Q is unique. So this part is unique. So Q is unique. R is also unique. Okay? So that's mean I give you a A and D, and then you produce these two unique numbers here. Make sense? So we call A a dividend. And should I write like this? Okay, maybe write as a list. So A we call a dividend. Q we call a quotient. Quotient is because, for example, like 6 equals to 2 times. Everyone goes wrong today. So you see, 6 equals to 2 times 3. So 6 over 2 is 3. So 3 is called a quotient. Okay. So we put a Q here. So we call it a Q. Okay. So Q is a quotient. And then D we call a divisor. Okay. So that's why we put a D here. So we take D and go and divide the dividend. Okay. Divisor. And then why R? R is the remainder, the thing that left over. Okay. So this leftover, of course, cannot greater than 2, right? So if it is greater than 2, we can just factorize it in. Okay. So that's why we got this condition here. R is less than D, right? So if R greater than D, we can put another D in. Okay. Okay. And then some notation is Q equals to A divide D. Okay, this one less used, but worth to take note. And then the most used one later is R equals to A mod D. Okay. So if I ask you, what is example 7 mod 2? So it's 1. Okay. So take the remainder. So something mod D is take the remainder of the dividing by D. Okay. This one you need to remember, so later we will use it quite often. This one maybe not for this section. Okay. Yeah. So since we got this uniqueness property on Q and R, okay, we can define modular arithmetic now. So we can do congruence. So what's that mean? So let's take two number. Okay. So how this two number is related by the other number? So let always we consider the m to be positive. Okay, positive. Okay. Then a is congruent. And what's congruence mean? So a is congruent to b. Okay. Modulo m. Okay. Congruent to b modulo a number. What does it mean? If m divides a minus b. Okay. So see this definition here. So what does this mean? This means m divides a minus b. I already told you what is dividing means, right? So that is okay. So the notation is m divides a equals to b. Okay. Which is a minus b equal to some integer times. Okay, you realize that maybe sometimes I put k here, sometimes I put k here. It's because z is commutative. So I can put left and right. Okay. Next. Okay, so we will write a triple sine mod m. Okay. Last time you saw this is in the logical equivalence, right? So now I use it on number, and then I have a mod m here. Okay. And then this term here is a modulus. Okay. And then the whole thing here is a congruence. Okay. MOD is a short form for modulus. So if A and B are not congruent mod M, we write A not equal to B mod M. Okay. Okay, so just now you remember I introduced another term like A mod M, right? So this term and this term is different. Okay, so this is the remainder after you divide by M, right? So this is the R such that A equals to Km plus R for some K. Okay, but what is this here? So this you need to take the difference and then look at the divisibility by M. Okay, so actually there's a relation between these two things. So there's relation between these two. So should I side first? So put size. So this one just put as a remainder. So what's the relation between these two? So let A and B be integer again. And M is a positive one. Then A congruence to M if and only if A mod m equals to b mod m. So that means their difference their difference is divisible by n if and only if their remainder after dividing by m is the same. Okay. So for example, I want to ask a question. So I ask a question. Whether 17 is congruent to 5 mod 6 or not. Okay. How do you check? One way to check is you check whether 17 minus 5 is divisible by 6 or not. Right? So this is 16 over 6, which is 2. So it's divisible by 6 because it's an integer. Another way to check is straight away check on both of them. So what is the remainder of 17 divided by 6? Divided by 6. 5, yes. So 17 mod 6 is 5. But 5, of course, 5 there's smaller than 6, so the remainder is automatically 6, right? Because 5 is 0. Wait, let me write it clearly. Wait, so 5 is 0 times 6 plus 5. Okay. See how many slides. Okay. I still got time. So okay. I got time, so I can go on. So let's try and prove this. Okay, these proofs supposed to be straightforward proof, nothing fancy one. So if you have some confusion, you should point out the spot. Okay, proof. So let's go one direction first. Let's go one direction, this direction. Okay. If the remainder is the same, then the difference is divisible by m. Okay. So then suppose a mod m equals to, this is a real equal. Okay, so notice that this is a 3 line equal and this is the real equal. Because why? Because this is an actual number. Okay? So in the actual number you can talk about equalities. But this one, what is equal means here? So the equality means here is you take the difference of these two, okay, and then write it as a multiple of m. Okay, so this is the difference between the equal sign here. So suppose they have the same remainder. So we can write what? We can write a equals to maybe what? Tm plus r. Okay. For actually it's a unique one, right? So it's the unique Pn r set. Okay. This is by why I can write this. Okay, so you need to justify why you can write this, right? So because this is by the division algorithm. Okay. I didn't tell you why is it true, but you need to use it here. Okay. Okay. Similarly, yeah, we can write E equals to Qm plus R, right? Because we say that the remainder of A divided by M is the same as B divided by M. So they have both have the same remainder. Okay. So this is Q Z by division algorithm again. Okay. Then what is this? Okay. So this is equivalent to A minus B M divided A minus B, right? Which is A minus B equals to some multiple of H again. For H. Z. H and Z. Okay. So since we have two ways to write A and B, then we can try and compute this. Then we get A minus B equals to PM plus R minus QM plus R. Okay. Which is PM minus QM plus R minus R, which is PM. Can I jump? Factorize. Okay. So you write A minus B in terms of sum M times sum. Okay. And M divided A minus B, which implies A is congruent to B mod. Okay. So if let me think. Yeah. So if you write like this, right? So if you don't put so this is notation. So if you don't put this bracket here, I think I should understand is this, right? Because if you understand this as this number here, so this number here is a remainder, is an actual number. That means you can't use this. You can't use the triple equal sign. Okay, because triple equal sign only makes sense if these two number here, the side by side number here, is equal up to modulo m. Okay, so I think should be fine if you write this or write this. Okay. So you should know that if I write this, it's actually mean this, okay, with a bracket, because it doesn't make sense to write only this. Okay, you cannot write this because this doesn't make sense. Okay, it has to be modulo, maybe modulo 2. Okay, because these two are what? Or 1 modulo 2, for example. Okay, so this line makes sense. Okay, so these are notation. So let me put it here, notation. Notation. Okay. So how about the other direction? Can you do it? Okay. Maybe left as an exercise, so you can try the other direction. Also straightforward. Just step by step. Just use the definition and then put them together. Okay. So the direction exercise. Okay. So you start with this and then go and find the remaining. Okay. Next. So next theorem. For this theorem for. Okay. This theorem is talking about how you express a number. So if m is positive integer, yeah, then a is congruent to b modulo m. Yeah. If and only if there's just a k that such that k minus b plus k. Okay. This one should be obvious to you, right? Oh, okay, again, okay, I write this as a proof sketch because I actually it's a proof, but I just don't put a full sentence here. So because so if it is congruence modulo m, that's mean a minus b is divisible by m, which is a minus b is a multiple of m. Okay, so you just move this around, then you'll get this. Okay, and then this direction, you just move the b to the other side. Then you can get this direction. Okay, so just moving b around, you will get two directions. And move forward, move to the right hand side, and then move to the left hand side. You will get this statement here. Okay, and then this statement will come in handy later. In theorem 5. Okay, so we try to study the structure of this modular number here. So this m is also positive again. Okay. So you always modulo a positive number, never negative number. Okay. So if A is congruent to B mod M and C is congruent to D mod M, okay, then then what you can do? Then you can do A plus C on the left hand side, and then on the right hand side you can do B plus D. Okay. Okay. And also similar with the product. Okay. Okay, so throughout set theory logic, you will see that we like to add things together. We also like to study the things that multiply together. Okay, these are two natural operations that we want to do. Okay, this one also easy. So you can use the similar method and then prove it. Okay. So I leave it as an exercise. Okay, just open up, just use the definition. So we can add, we can multiply. And then the next one, okay, this query unravel the structure of this modular arithmetic here. So similarly, we have m always modulo a positive integer, okay? And then you got two number here. Then, okay, then you can add them together, okay, and then take the remainder first, and you can is equal to you take the remainder separately and then add them together and then take the remainder. Okay, so this one got more work. So if this is more work, then you can just do this. If this is more work, then you can do this. It depends on which one is easier. So I provide two ways to get the remainder. Notice that I use the two equal sign here because this term here is a remainder. This term here is another remainder. So they are equal as a number. Or I can multiply two numbers together and then divide it by m. Or I can do it separately first and then multiply them together and then you divide them. Okay, maybe you think that, hey, this one got more step, maybe use longer period. But imagine if you got maybe billion digit, multiply them together. Maybe the multiplication will take more time. Okay. So you can do the division on individual terms and then do it again. So get easier. Okay. So this proof also left as an exercise. Okay. So to prove them, you just unravel the definition. Okay. So what do we achieve before we go into rest? So what we have here is we can define a set of Zm. Sometimes we also call it a Z mod MZ. Z mod MZ of Zm under script. So this set here contains number 0, 1 up to m minus 1. Okay, sometimes we call them equivalence classes, right? Because for example in 0 we will have m, 2m, 3m, or minus m, minus 4m, for example, and so on. Okay. So actually this is a set. Okay, this is a set. As a set. Okay. So what can we do to them? So we can add them together. Okay. How do I add two numbers together? So when I add them together, I take their remainder so that they fall back into this set again. Right. Remember the remainder have to be less than the divisor. So this is the divisor. So it will always, when you take remainder, you always fall back into this set here. Okay. Similarly, if you multiply, you also can define the modular multiplication. So a minus b mod m. Okay. And then there are nice property that they satisfy. For example, they are close, like integers. When you multiply two integers, you add two integers, they are still the integers. So if you take if a and b in the set, okay, then you can multiply together, you can add them together, it's still in Z. Okay, like literally like the integers. Also associativity. So remember, like you can do A, B first and then do C, or you can do B, C first and then go A. Similarly for the similarly, let me write Similarly for the multiplication by M, okay, and then commutativity, like what I said just now. So A plus B equals to B plus A, or A times A, B equals to B times A. So this is also like what the integers have, For example, you got the identity elements. Remember I talked about identity elements in I think set theory or logic, both of them. So for example, you got 0, A plus the 0 is equal to itself, and then A times 1 is equal to A. Okay. So 0 is the we call it additive identity, and then this is called a multiplicative identity. So this line have to work for all A and B. So I don't include, keep writing it. So you should keep writing it. Okay. And then yeah. And then also share yeah, so these these also shared by the integers. Okay, you can see it. You can check it yourself. And then what else? Also have the additive inverse. Okay, what does this inverse mean? So additive inverse means so there's a number, there's a m in Zm such that for such that there exists. Okay, I do the other way around. So for every a in Zm, and there exists, and don't use m anymore. Use p in Zm such that a plus in the modular sense, p equal to 0. You know what's p? What p works? Try think what p works. Yeah. What p works? So a plus something, okay, is equal to 0. So let's unravel this. So this is equal to a plus p mod m. Okay, is equal to 0. What number you should put? Hmm? What number should you put? Hmm? What number should you put? Ah, how to get 0? You know how to get 0 first? Huh? Huh? Okay, how to get 0? So um so how to get 0? So what's the number that when you divide you get remainder 0? Huh? What? Huh? What's the number you get? So what's the number? Let me see. So how should I say? So what's the number? What is the number k? Okay, this one is the last question. Then we go to the rest. Okay, try focus last. Give me two minutes. So what's the number k that when you divide by m, you get 0? Huh? Why like this question a bit stupid? Huh? What's the number k? Huh? M? Oh, m is this divisor. Hmm? Huh? K? Dm? Right. Multiple of m. So all the multiple of m will get sent to 0 mod m, right? So for example, mod mod 7. Okay. So what are the numbers that are congruent to 0? So for example, 7 mod 7, right? For example, 14 mod 7. Okay. Okay, makes sense. So what can you put here is a plus what? Huh? How to get 0? Hmm? Minus a. Okay. You need to minus a plus m. Minus a plus m. Yeah. Yeah. M plus minus m. Okay. So you get 0. Okay. And then let me let me okay. And then the last one is distributivity. So it's like how you distribute the n and o. So this one you can distribute a times b plus c, which is a dot b c. Okay. So wait, this one the name I have to give you. So these three. So these 5 properties shared by integers, and this modular arithmetic. So sometimes we will. So I mean, they share the similar structure with integers. Okay. Any question on that? If not, we take a break until 5:08. Then we come back. No, 5:13. Sorry, 10 minutes. Okay. 这个是说这个意思。如果是七的话，就是可以被七成这个。这个横向啊，这个横向就是因为我说这个其实是一个集合，就是一个 set 来的。这其实本身是一个 set，就是说什么东西存在于这个 set 呢？就是比如说零的 set 里面有 m 的倍数，为什么呢？因为余数就对，所以这个的话就是 m 加一，2m 加一，对，没有错。 对，对，你就会拿到对，
就是这样的。
对，
然后它就是这种。那如果是7的话，也就是然后一直到6。
啊对，没错没错，
然后那这个 M 有没有就是
嗯什么叫固定呢？就是说你
哦，行，那我大概
呀
理解。那
呀，
后边这个大概是讲什么？
这个哈，这是说它跟那个一个就是有相同的性质，就是说，比如说我把它们加在一起，它们乘在一起，它还是在投在这个里面。就是说我把两个东西加，就是合在一起过后，它不会跑去其他。
比如就这个，
嗯啊哈，这个怎样？
是两个等价的意思。
这是我定义的，这是
这两个
定义啊，不是等价，是定义。就是说我写这个什么意思？就是我要把它们加起来，然后我取这个模。
哦，那这个是什么意思？
哪一个？
就是这个，嗯，
诶，你是说，哦，这个是一个这是一个 subscript，所以这个是在下面的。
对啊，
哦，因为我活的世界，我要告诉你我是末级嘛，对不对？
嗯，
不是，我要告诉你，对，我要告诉你我是末级，就是说这个 M 很重要，对于这个加，
嗯，
所以我要把这个 M 记在这个加这里，
哦，相当于
明白吗？
这个就是这个的意思，对吧？
对，
哦
所以如果你真的要看这个是这样的，
，OK，
这个 M 跟
那你
B 呢？
后边再说什么？
嗯哼，
就是你讲的要提这个后边这个，但是这个是想说什么？
哦，我想说就是它每一个东西加了一个东西过后等于零，就比如说二加一个号码可以得到零，是减二，
对，
对，但是不是只有二有这个特性吧？所有号码都可以，你只要加
一元的上半组，
减一，然后这个情况就是你可以取这个 a 加 m 减 a，或者应该减 a 也够，
直接减 A。
对，也够
所以这个东西到底是什么？
啊。
这个到底是什么东西来的？就这个东西是什么来的？就这个。
那我跟你说，为什么减 a 在这里不太好看，是因为在这个世界里，不是没有减一，不是说没有减一，就是
只有这个过程。
对，我选正的来表示它们。所以如果我选 m 减 a 啊，它肯定是正的，因为这个 a 肯定是小过这个 device 这个 m，所以我拿大的东西减小的东西，它肯定是正的，你明白吗？对
所以这个 M 不影响范围，它只是标在这里，图形里有一个这个数字，是吧？
对，对，因为这个加法很对这个 m 敏感，如果我换 m 的话，这个数就不一样了，
嗯
这出来的数就不一样，
嗯，
对吧？有
好，其实那个
啊哈
M 是代表我们 module 的什么？
啊，对，
然后它是有代表一个数目还是什么？就它
怎么说？
呃，
谁是一个
这样
数目？
就是这么会有这个 M
这个 m，
啊？
这个 m 哈，因为如果我换这个 m 的话，这样这个东西算出来的东西是不一样的，对吧？
这样它跟没有 M 是什么差别啊？
你是说你是说这个？你是说比如说
就
这个
A 跟 AM
这个 a 跟 am
啊，就 A 跟 A modulus 有什么差别？
听不懂？a
就是它不
不然你有一个
是不是
例子，
有个好像哦 M 就有 M 跟没有 M 的有什么差别啊？
比如说这个没有 m 啊，这是没有 m，是你指的没有 m，
就有 M 的符号跟没有 M 的符号。
我是不是少了一个 m 的？ 少了个，这样子，什么意思？是吗？你说嘛？你说这个和这个，这个和这个，还是这样？
这个是加跟乘的
对不对？
啊，就这两个啊，
这两个怎么差？这两个怎么差？所以这一个的定义是说，我这个加是正常的加，就是你知道的加，就给你两个号码，你就可以把它们加在一起。
然后有一个 m 的是
有一个 m 呢，是你把它们正常加在一起过后，你取 mod m。
哦，所以那个 m 它只是我加跟乘而已，就像 a b 那种是没有 m 的。对，这个
有这个 a 跟 b 是活在这个世界里面的，这个 a 跟 b 是活在这个世界里面，所以它是这些号码吧，0到m减1。是你要的，
但是现在
它是这样。
对，就像是
OK。Hello, hello. Hey, hello. Yeah, yeah. You want to ask? You can ask me. You want to ask? Mm. Sorry? Yeah. What? More? Next break ah. This break lah. Now lah. Now. Ask now. What? Okay, okay. You tell me first and then.
怎么用维恩图来理解这个？
Venn diagram.
嗯，
这个 this one is proposition. This one is set theory.
就是维恩怎么说？
Venn diagram.
啊，yes，I want 就更加直观一些，的，就这个可以这样理解吗？系，然后就是这样画一个图，比如说这个是 G，这样吗？可以画图理解吗？这个，
对，我再回答你。我跟他们全部在一起。你做菜系听过。
谢谢。
Okay. Okay. Yeah. Okay. I think she asked. Okay. Actually, you should ask. This just now during the start of the lecture. 最好问这些题目在那个 lecture 开始之前，所以才不会突然间有点跳戏。Okay. Right. So she asked about G implies H. Can you understand this as a set theory? So can you use Venn diagram to draw G imply H? This question, I think, ever since I taught the proposition logic, a few students already start thinking whether this is related to set theory or not. And then this student here, she draw something like this. Okay. I think you can show that this doesn't work for G implies H. Okay, so this one doesn't work. You have to show this doesn't work. So one way I suggest is this part here. Okay. maybe this part here will suggest how to go to set theory. Because we have definition for negation, which is the complement, okay? And then we got OR. So OR is the union, okay? So what I think is true is for this diagram here, okay, maybe you can draw, okay, this is the universal set, and then you draw a G, you draw an H, okay, so this is a G, this is a H. So it's everything outside or H. So everything outside or H. I think this is G implies H. Maybe you can try and check. Is that okay? Okay or not? Okay. You got a question? Left? You mean which left? This left? This one? This one, I mean, how to go from here is to go from here to here. This is what I mean. I mean, to go from here to here is going from here to here. This part has set theory interpretation. Okay. 因为这里有集合的那个，我没有，我怕听不懂，等下，因为，但是我也要讲英文，所以就两个都要说，因为，对啊，这知识的传输就是这样，所以没有办法，这是过程，所以，所以这里有集合的意义，但是这里没有集合意义 ，OK， 所以我是想透过这个等价来，构造这个集合的意义，这个，因为本身这个是没有集合意义 ，OK， 但是这左边和右边是一个等价方式 ，OK， 可以吗？理解一下 ，OK， 有问题再问 ，OK。So yeah, so whenever you ask question, then you try listen, and then if you can't digest it, then you can keep on meditate, and then you got new question, then you ask again. Okay, just now I think quite a lot of you confused with this, but not to say it's not important, but it's structure that you can observe from this modular arithmetic. Okay. So yeah, okay. What's going on? Okay. Okay, maybe I don't want to explain. Let you ask me questions. So, so you, okay, if you are blur about this slide, right? You go back and think. You still can't think thoroughly. You can bring it up next lecture. Okay. Bring out next lecture. So let me create a program for you. Okay, next. So next we want to talk about primes and greatest common devices. Hey, why you guys keep talking? Discussion. No, it's not discussion. Discuss during tutorial time. Okay. So we want to talk about primes and greatest common divisor. So in this subsection, we want to break down the numbers, okay, into products of numbers. So we are interested in these numbers, which are called the primes. So what is a prime? So it's the integers, okay, which is greater than 1. It's called prime. If the only positive factors of P are 1 and P. Okay. And then, okay, let's go to example and then we go to next. So example, 2 is a prime. So 2 is the number that is greater than 1, okay, first of all. And then the only number that divides 2 is 2 itself. So it's 1 and P. Okay. So similarly, like 3, 5, 7, and then can you go on? 11, 13, and then 17. And then you can keep going. Okay. Upfront. Okay. So, and definition, and another one is, so you got prime, also you also got non-prime, so we call it a composite. It's called the composite. So for example, 1 is not, wait. So 1 is not prime is here, okay. 1 is not composite and also not prime. So maybe we write it down here. So it's not composite, move it down. So it's not prime. So 1 is not prime and not composite. Okay. Why is it not prime? Because it's not greater than 1 even, right? Okay. Not greater than 1. And then, for example, what is composite? For example, 6. So other number here, for example, 2, 6, 8, right? Because 4 is like 4 divided. So 1 divide 4, 2 divide 4, 4 divide 4. Okay, so you got more than 2 divisors, 2 factors. Okay. For example, 6, you got what? 1 divide 6, 2 divide 6, 3 divide 6, and then 6 divide 6. Okay. And then you can do exercise for the other. Next. Okay, next. So this is the fundamental theorem of arithmetic. Okay. So the statement says that every integer greater than 1 can be written uniquely as a prime or as the product of 2 or more primes. Okay. So after you break them into primes, then you can order them in a sequence. So maybe you can order them in a non-decreasing sequence. I think this proof Yeah, this proof is in the book, but the existence proof. So there are two part of this proof. Maybe I just proof sketch. So you need to prove the existence. Okay. Meaning every number you can break into product of primes. Okay. Every integer can be written as a product prime. Okay, and then second, you need to prove the uniqueness part, the distant part, the uniqueness part. So the uniqueness part is to show that this product of prime is unique. Okay. This part can use the two. I can use two from this lecture. Cannot not. Maybe cannot because there's one slightly technical part. But you need to use induction, a different induction for existence part. But if you are interested, you can go and look at the textbook. Okay. Okay. The next theorem is useful. Okay, this one you should know, I think. So this theorem is useful. So if I give you composite integer, how do you find the number that divided? So how you break it into the product of primes? So one divisor you can find is the divisor that is less than or equal to square root n. Okay, so this one is proved by contradiction. Maybe you can refer to the book because maybe it's not very useful for the class. So this is proved by contradiction. Okay, playing some trick. So what is useful about this theorem is how you show that something is a prime. So for example, you want to show that 137 is a prime. Okay, so you just need to check the prime divisor that is less than square root n. So square root n, I think you can estimate with 144, right? So 144 is square root. 144 is 12. So you check the number before 12. Okay. Which is less than square root 1. Okay. So, but you can actually do the congruence modulo. So these are not congruence to 0 mod 2, 3, 5, 7. So it follows that 137 is the prime because only 1 and 137 divided. Okay. Okay. You know why? Because this is the contra positive of this statement here, right? So if doesn't have, then it is not a composite. Wait, what did I write? So it's not a composite integer, which is prime. So it's the contra positive of this statement. Okay. Contra positive. Okay, next one. So is the prime really helpful? Yes, because there are infinitely many primes. So prime never use up. Never, yeah. Okay, so we should prove by contradiction. Okay, I think this one you have to see because this is classic too. I think this lemma is called a Euclid's lemma. So Euclid is a very famous mathematician in old days. So proof by contradiction. So you need to suppose not this. Okay, there's no infinitely many primes. So there's finitely many primes. Okay, so assume for the sake of contradiction, Okay, let me pause for a while to pass this. Okay, so assume for the sake of contradiction, there's only finitely many primes. Okay. So finitely many primes, call them P1, P2, up to Pn. Okay, finitely many. Then we can consider Q equals to product of them. Okay, product of them plus 1. Okay, and then I want to argue that this is a prime. Okay, so why is this a prime? So why is this a prime? Give you maybe 2 minutes to think why is this a prime. We can discuss with your friend. Think why is it a prime? Yeah, now you can discuss, okay? Yeah, make noise. Okay, any idea? Any idea? So if Q is a prime, okay, then we reach our contradiction. Okay. Then we reach contradiction. Because we said that only finite many, but I produce another one. If Q is not prime, okay, what happens? That's mean then Pi divide Q for some I. Okay. Okay. Pi sum I divide Q. So Pi divide Q, right? And of course, Pi divide the product of P1 up to Pn. Right. So remember, we said that if A divide B, A divide C, A divide the sum of multiple of B and C, right? So Pi divide Q minus Pi P1, which is 1. Okay. So what divides 1? Only 1, right? And 1 is not a prime. Okay. So contradiction. Okay. Another contradiction. Okay. Because we assume that Pi is one of the prime. Okay. Contradict the fact that Pi is a prime. Okay. So yeah. So this is the proof of infinite many primes. But there's another concept. So it's a concept called the twin prime. Okay. Twin primes, what's the definition of twin primes? Is the prime that are the difference by 2. So for example, 3 and 5. Okay. So 3 is a prime, 5 is a prime, the difference is 2. And then for example, 5 and 7, twin primes, 11 and 13, 17 and 19, okay, 29 and 31, 59 and 61, and then keep going on. Okay. So the question is, do we have infinitely many twin primes? What do you think? What do you think? Yes. Why? Yeah, I don't know. This is open. So this is an open question. We don't know whether it's there are infinitely many twin primes or not. Yeah. So this is open question. Okay. If you solve this, maybe you can bring some new blood into cryptography. Okay. Yeah. Okay. Next. Okay. Next is GCD. So greatest common divisor. Let A be that again. Not both 0. Okay. So we consider the largest integer D such that D divides A and D divides B. Okay. It's called the greatest common divisor of A and B. Okay. And then we will write it as GCD of A and B. Okay. For example, what's the GCD of 8 and 64? Okay. So you need to find a divisor that divides both, and that is the largest one. 8, yes. So 8 divide 8, 8 also divide 64. Okay. So if the GCD is 1, okay, we will call it a relatively prime. Relatively, if GCD is prime. So for example, GCD of 3 and 2 and 3 is 1. And then GCD of, for example, 4 and 5 is 1. For example, GCD of 2 and 51 is also 1. Okay. So 43, I got 3 minutes. Let's see, I want to get into Euclidean. Okay. Okay. Okay, maybe I need to go to this definition first, because this is a setup for next week. So if we have a bunch of integers, okay, we also can compare them. Okay, we call them pairwise relatively prime. If you check all the pairs that the GCD is 1. Okay. Okay. Okay, next. So I talked about this LCM. About 5 minutes. I want to get into Euclidean algorithm. Maybe. Okay. Maybe. Can I? Yeah. So can I assign the reading for? Please read on LCM. So which is the lowest least common multiple. Okay. History on this section, and then the relation between LCM and GCD. Okay. How to get into Euclidean algorithm today. Okay, to do too many proof. Take a bit time. And then okay. So this one you definitely need to learn. I'm giving clue here. So you have to learn this. Euclidean algorithm. Okay. So the idea is how to find a GCD between A and B. Okay. To find a GCD between A and B, okay, first you can do the division algorithm. Okay. And then you can reduce it to the GCD between B and the remainders. Okay. So for example, you want to find GCD of A and B. Okay, you can take B, I mean the smaller one, to divide the larger number, and then you keep going. And then you take B and then do it with R, and then you keep going. Do the division algorithm. So maybe to say it's a bit abstract. So let me show you. So for example, I want to find the GCD of 51 and 9. Okay. So what you do is you write the division algorithm. So 51 is what? What times 9? How to do the division algorithm? This form. 5 times 9 plus 6. Okay, right? Because this remainder is smaller than Q, BB, sorry, smaller than the divisor. So this is the unique one. And then you can keep going on, take the B one, yeah, and then do it with R. So you take 9, and then you do it with the remainder. So how to do the division algorithm is 9 is equal to 1 times 6 plus 3. Okay, and then 6 equals to 2 times 3 plus 0. Okay, and then 3 is equal to 1 times 3. Oh, done already. Right? So 3 is equal to 0 times anything. Okay. Okay, so you can stop here. So that's mean, okay. So this means that this implies that GCD of 51 and 9 is equal to GCD of 9 and 6, which is equal to. So this one, okay. So how you apply this? You need to do the division algorithm and then keep going on. So and then GCD of 6 and 3, am I right? 9, 51 and 9, and then 9 and 6, then 6 and 2, which is equal to 2. Okay. Okay, so this is how you find the GCD. And then the next one you need to learn is called the, okay, you can, to prove this, you can refer to textbook for the proof. Okay. But the way how to find GCD, you should know. Okay. Next one is called the extended Euclidean algorithm. Okay. What's the extended Euclidean algorithm? So if A and B in a positive number again, then there's this S and T such that okay, you can express actually the GCD of AB in terms of A and B, the sum of multiple of A and B. Okay, so how to do this? Okay, for example, okay, instead of proving it, I just show you this method here. So you can work out the proof yourself if you want, or read the proof using the example I gave. So for example, write the GCD of 51 and 9 as a linear combination of, okay, I want to use this word. Right, GCD of equal to S times 51 plus T times 9 for some S and T in the integer. Okay, so it's actually the back work. You can understand as a back work of this Euclidean algorithm here. So let me show you how to do it. We will have an exercise in the tutorial section, so you can try a lot of them to practice your skill. So the GCD of 51 and 9 is 3, right? Just now we found it. Okay. So using the backward, so it tells you that 3 is what? 3 is equal to 9 minus 6. Okay. So 3 is equal to 9 minus 6. Okay. So here there's no proof. This is just algorithm. And then you can express 6 with 9 and 51. So 6 is 51 minus 5 times 9. Okay. So you just expand it out. So you get what? You get minus 51 plus 6 times 9. So you can take s equal to -1 and t equal to 6. Okay. So this is the two things you need to master. Okay, need to master these two. Maybe I'll mention the other two, lemma and theorem, and then you can try to prove them. First of all, any question on these two methods or not? Any question on these two methods? So first method, you just do the division algorithm, okay, using the divisor and the remainder, okay, until you get to this last step here, and then you can decide what's the GCD. And then if you want to express the GCD of two numbers as the sum of multiples of two numbers here, then you can do the backward Euclidean algorithm, which we call the extended Euclidean algorithm. Okay. And then I'll mention two lemma here, lemma and theorem, and then we'll stop. Proof, you can try and prove yourself, not too difficult. If you reach any difficulties, you can see the textbook, or next week bring it up, and then I can show you. So if there are three positive numbers such that the GCD of AB equals to 1 and A divide BC, okay? So this means what? A doesn't divide B, and also they don't have common divisor other than 1. Then the result is A divides C. Okay. So if A and D doesn't have common divisor greater than 1, then if A also divide BC, then A will divide C. Okay. And then this will go back to this modular arithmetic to simplify our expression. Okay. So if M positive, okay, this is the usual condition, A, B, C in Z. Okay. Suppose AC congruence to BC mod M, and the GCD of C and M is 1. Okay. So both of them are product containing C, but C and M, they don't have common divisor greater than 1. Okay. Then you can just safely cancel them. Okay. So this is a easier help you to simplify the congruence. Okay. Then next week we will learn how to solve the congruence. So this proof you can you can refer to this. If you have question, then next week at the start of the lecture, I can show you how to do if you ask. Okay. Refer and exercise. Okay. These proof are just like spell out the details. So this is lemma, right? So this is theorem. So that means you need to use this lemma to prove it, the theorem. Okay. Okay. Any question before we go into the break? No? Okay, just we will come back at 56607. Huh? Okay.
Walk around.
就是如果说就是这个 Z M，
Yeah.
它是不是就是代表是0到 M 减1会有整数的积分？
再说一次。
就是这个 Z M 就是代表0到 M 减1所有整数的积分。
什么叫做0到 M 减1所有的奇数的？
就是比如说1等于6的话，那就是0到5，0、1、2、3、4、5的集合。
对。但是但是我写这个干呢，意思说，你可以把这个0到5不是本身当做成一个集合，对吧？
那这个0上面杠一下，对，为什么会等于这个？
因为为什么哈？因为 OK， 因为这些都是被 M 除后剩余0的东西，剩余0的号码，对不对？对吧？
那就是它上面多一个杠，就是代表什么？
代表是你可以理解这些数字为一个集合，它不只是数字，它也是一个集合，很乱的，就是可以理解它是一个集合，可以理解哦。
就是上面有一个杠，是一个集合。
对。
就是认出它是，就是只要出这里。
就是这里这个集合，在这个集合里面的东西是什么嘛？对不对？这集合里面的东西是那些被 M 除后剩余0的东西，然后这里面是什么呢？这个是被 M 除后剩余1的东西。
对。
OK，就拿你刚才说F 开始说，比如说这个0里面有什么？0里面有0、5或者减5、10等等。1呢？有1、6、6、7等等。
Teacher, may I ask?
Yep.
How this one multiply 6 become? Is it this 5 multiply 9 or is 5.9?
5 times 9，
就我看不懂，就它这个是讲变的。
就用这个
乘9加6。
所以它这个是1乘6来的。
对。
然后6变。
对。
所以是这样子，然后搬过去。
对的。对。
OK。
对。
看这个。
Yeah.
Yes, thank you, teacher.
Okay. Yeah.
This one.
Multiply
M is 0, M is and then so
yeah. Multiply.
Multiply.
Yeah.
Yeah.
It's not equals.
What do you mean?
它们不相等的话，怎么个运算？
你说如果 m 乘 k，然后乘
k 乘 n，
说
嗯，
什么不相等
就是他们的 m k n 这三个数，就是本
？m
来
k n 三个不相等，
他们是这样的，就是
加的话不行，乘的话可以。
乘的话就是不相等也行。
可以啊，诶，这个不是不相等，这个是不相等，是你说的不相等。
所以就是数的和它的 row 是要一样乘的。
第一个的 row 和第一个的 column 和第二个的 row 是一样的，就可以说
就可以
说。
然后乘的话就是
对
一对应的。
对，
再 plus 加起来，
没错。Okay, everyone's back. Okay. Just now I got a question on where to get the 6 here. So all this substitution is based on the backward substitution here. So if you want to find 3, okay, there's a phrase, there's an equation here that containing 3. Okay. If you want to find 6, there's another equation here containing 6. Okay, and then you keep going up, and then you will reach the equation that contains A and B. Okay. Okay. So we will do quiz now. So please turn off your laptop, close it, and then face down your iPad and phone. So make sure when you get your test, remember to write down your student name, student ID. And then I need can anyone close the door, back door? Thank you. Can I get one person from the first row to count how many people in your row, and then come and collect the test paper from me. Okay, 18. Okay. 18.
8. Oh no.
没有就 8. times 2啊，yeah，全部 yeah，15个15，so you got 16, right? Times 2. Yeah, yeah. The whole 16, okay. 15, 17. How about you? Huh?全部 Yeah. Yeah. So you can read, but don't start first when you get the quiz. You can read, but don't start first. You can read, but don't start first, huh? Okay. Don't start first, huh? You can read, but don't start first. Wait until everyone got the paper. Don't start first. Please don't use your phone. Close your phone. And then also don't disseminate this quiz because someone can't come to the class. Have to do online quiz as well. Wait until all the quiz are marked. And what else? And then we will spend 15 minutes. Okay. We will start now. 6:25 will collect the paper. Okay. Some correction to the question. 2.2. I should say find domain interval such that f is bijective onto the onto the corresponding range. Okay. So maybe you confused. Yeah, I think it's right to confuse. So you fix the domain and then you look at the range and then ask whether it's bijective or not. Okay. So maybe it's confusing. So I give you another 5 more minutes. So I just check the bijectivity on the range, not the original column. But if I want to check on the column notation, but just make it easier. And 1 minute to clean up. Make sure you write your English name on the paper. And then make sure there's uni ID, English name. Then once you're ready, you can just pass to the front. And then the first person will count the number whether it's the right number or not. Okay, once you're ready, just pass it to the front. And then you can start do the tutorial question. Just pass to the front. Pass it to the front. Yeah. Pass it to the front. And the first person also check the name also. Every make sure every sheet has their names and ID on it. And then match up with the number you told me just now. Please pass to the front. 15. 16. 16. Okay. Huh? Check. 17. Okay. Thank you. Okay, 2. Okay, 2. Uh, 16. Yes. Okay. Thank you. From where?
I don't know.
Huh?
The person from my back
Which
passed it
group?
to
Which group?
this one.
Huh? This one? Hello, hello. Hey, why there's 3 extra? Huh?
What?
Why there's 3 extra here? I thought you said 22.
22呢？
22为什么有3个多出来呢？
啊？那是不是？
也只有21啊。还没算。对。啊？
Testing.
Yeah, we have 4 minutes before dismiss. Do you think the quiz is hard? Yes. I'll show you the answer after the marking. And I think it's not maybe. Yeah. I'll show you the working after the marking. Hopefully we'll be get the marking back next week, then before the exam. One is harder or 2 is harder? Huh? Both. Okay. Both. Okay, I'll see. Okay, since this quiz is so hard, so I will give you a hint. So 4.3.32, you must master how to do it. Huh? 4.3.32, you must know how to do this kind of question. And then what question we have? And then 4.3.40, you also must know how to do. Okay. Which is the last 2 algorithm we did in the lecture? The Euclidean algorithm and the standard Euclidean algorithm. Must know how to do. Okay. Yeah, you ignore the instruction in your textbook. You just use the algorithm I did in the class, the Euclidean algorithm and the extended Euclidean algorithm to do the question. Okay. I think in the textbook, the extended Euclidean algorithm is a bit different. The one I taught in this class is, I think it's another method in the textbook. It's not called the extended Euclidean algorithm. But when I learned it, what I did is called extended Euclidean algorithm. So just use what I do in the class and then write in the exam using what I did. Okay. Okay, and I will post the solution on Thursday. Then you can check the solution. Anything to ask? Huh? Any question you want to discuss or not? Haven't done yet. Yeah, you can try first and then can refer to my solution. And then any question can bring on next lecture. At the start of next lecture. Then we can discuss.